Rightio then. So this is going to be your lesson 17 video. This is going to be the first part of our fourth and final unit here in this Algebra 2 class. What we're going to talk about in this first lesson is factoring polynomials. So we've done a lot of factoring, but it's all been with quadratics. Now we're going to go ahead and apply what we've learned with quadratics and learn a little bit of new things. But we're going to use all of those factoring strategies here again with higher degree polynomials, so beyond degree 2. Okay, so here's our EQs. We're going to talk about finding linear or quadratic factors from a polynomial using grouping. Then we're going to talk about how to do the same using sums and differences of cubes. And then we're going to briefly discuss the Fundamental Theorem of Algebra, which it comes from all of this that we're doing. We're basically going to be leading into it. And then, using basically the fundamental theorem, we are going to work our way backwards from the factoring and figure out how to derive polynomials given an nth degree and a number of roots. Okay, so let's start with how we can factor just using grouping. So we've already seen how to use grouping, and this is just a nice, cute example to motivate what it is we're going to be doing. Okay, so here we've got a function, f of x, okay, and we see that there's, well, how many terms? So that's the first thing we're being asked. So there's 1, 2, 3 terms, and the terms are all separated by either a plus or a minus. That's how you can count how many terms you have. Okay, the first term is a product of x squared times x minus 3. The second term is the product of 2x times x minus 3. And the last term is a product of negative 3 times x minus 3. Okay, so it's got 3 terms. Okay, what is the GCF of this function? Well, our GCF here is simply this x minus 3. Okay, that's the greatest common factor all 3 terms have in common. Okay, so number 3, third thing we're being asked to do here on this example, factor f into a product of a linear expression and a quadratic expression. Okay, so we need to factor it into the product of a first degree expression times a second degree expression. And we can do that just by factoring out our greatest common factor that we found on number 2. So if we go ahead and do that, we factor out x minus 3, that's going to leave us with x squared plus 2x minus 3. Okay, so we have a product of a linear factor times a quadratic factor. Okay, and fourth thing we're being asked, factor it further into a product of only linear expressions. Okay, so only linear expressions. So we only want first degree terms, and that's going to be relatively easy to do because we know how to factor quadratics. So we can take this guy and just use AC grouping. AC is negative 3. Okay, what are the factors of negative 3 that will add to positive 2? And that's simply going to be 3 times negative 1, or 3 plus negative 1. Okay, so we're going to split the bx term using what we just found. So we're going to say plus 3x and minus x minus 3. And we group. And then we factor. So here on the left, our GCF is going to be x. That leaves me with x plus 3. Here on the right, we don't want a leading negative coefficient, so we're going to factor out a minus 1. That also leaves me with x plus 3. So my final answer here is all of this is simply equal to x minus 3 times x plus 3 times x minus 1. Okay, we factored out this x minus 3, leaving us with the x minus 1 here. Okay, so in a nutshell, that's basically what we're going to be doing. Okay, so now let's apply that on a little bit more difficult examples, and I guess I can just keep using the same color here. So let's go ahead and start just grouping. So we're being asked to factor h, basically kind of the same way that we did here on this earlier, simpler example. Right, so let's go ahead and group. Okay, so I'm going to factor out the GCF from both. And you're going to see that this won't always work. You may have to move some of the numbers around to get it to factor the way you want. It just depends. Okay, but on these simple examples, we're just going to leave it like that so I don't blow your minds. Okay, so my GCF here on the left is going to be 3x squared. And I'm left inside with x plus 3. My GCF on the right is just going to be 4, so I factor out the plus 4. And I'm going to be left with also x plus 3. Then you guys know the drill. Just factor again. That's going to leave me with x plus 3 times 3x squared plus 4. Okay, and that's as far as we can factor that guy. And I mean, we could kind of factor it further, and I'll show you an example of that here later when we get into the fundamental theorem, but again, don't want to break your brains just yet. So let's go ahead and factor m now, same idea. So we're going to group. Okay, we're going to factor. So our GCF here on the left is going to be 2x squared. And that's going to leave me with x plus 5. My GCF here on the right, we don't want that leading negative, right? So we're going to factor out the minus 3. And that leaves me with x plus 5 again. And we can factor further. We're going to factor out the x plus 5. And that leaves me inside with 2x squared minus 3. Okay, so you can see this is pretty simple and straightforward. Okay, and again, it's not always going to work out this simple. Okay, this is just to kind of really illustrate a point and let that point really hit home. Okay, so same idea. We're going to group and factor here on n of x. Our GCF here on the left is going to just be x cubed. Okay, and inside I'm left with 4x plus 7. GCF on the right is just a plus 1. And that's going to leave me with 4x plus 7. Okay, when I factor again, I'm going to just have 4x plus 7 is my GCF, and that leaves me with x cubed plus 1. Okay, so not really anything new here. Okay, where it starts getting new is when we start applying sums and differences of cubes into this. So now we're answering EQs 2 and 3. Okay, so a sum of cubes is this guy right here. So one number cubed plus another number cubed. So that is literally a sum of cubes, right? So a cubed plus b cubed. This can be factored into this. Okay, so a cubed plus b cubed can be factored into a plus b all times a squared minus ab plus b squared. Okay, analogously, you've got differences of cubes. Okay, it's the same idea, but you're going to notice something, a little something changes. So a difference of cubes, obviously, you're finding a difference between two cubes. This guy can be factored into this over here. So a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. Now you'll notice, okay, these formulas look really similar, but there's a key difference here that we need to take note of, and that is this minus sign and this plus sign here. Okay, so when we're doing a sum of cubes, we're going to have plus and then minus. When we're doing a difference of cubes, we're going to have minus and then plus. It's going to get switched. Okay, so it's really easy to mix these up. Make sure and write them down. But obviously, remember that trick that I just showed you. Okay, it's going to help you avoid those kind of goofs. Okay, anyway, so let's go ahead and practice factoring this way with a few examples. So number one, we see we have x cubed plus 27. Well, this is equivalent to x cubed plus 3 cubed. So this is a sum of cubes, right? And it can be factored this way. So a cubed plus b cubed is equal to a plus b times a squared minus a times b, right? And in this case, it was b times a. But we always like to put the coefficient in front of the x, right? Plus b squared. So 3 squared or 9, sorry, 3 squared or 9. Okay, so that one was a sum of cubes, easy peasy. Okay, let's get another one. And if we wanted to, we could factor this guy further. Okay, but the instructions say just the product of a linear factor, and a quadratic factor. Okay, so we're not going to worry about, we could factor this quadratic even further into two linear factors like the x plus 3, but we're not going to get into that just yet. Okay, so now we see we have a difference of cubes. Okay, x cubed minus 8 or x cubed minus 2 cubed. Okay, same idea, except the plus and the minus are going to get flipped, right? That was the pattern we noticed a second ago. So we're going to say x minus 2 or a minus b times a squared plus, right, plus this time, plus a times b. So that's going to be 2x, right? That's b times x or a times b. Okay, and then we're going to do plus b squared. So 2 squared would be 4. Okay, let's do another one. So we've got 27 plus 125x cubed. Or, and I'm going to go ahead and flip this to where the x is first, because that just bothers me. Okay, so I'm going to go ahead and rewrite this. So 125x cubed plus 27. We can rewrite that as 5x all cubed, right? Because 5x times 5x times 5x, that's going to give me 125x cubed. Okay, anyway, so a cubed plus b cubed. We already saw that 27 is 3 cubed, right? So that's how we're going to rewrite this guy. 5x all cubed plus 3 cubed is equal to, and again, we have to account for the plus and the minus flipping places again. So a plus b times a squared, so that's going to be 25x squared, minus, so that's going to be 5x times 3, so 15x, plus 3 squared, which is 9. Okay, one more example. And we're just kind of flip-flopping. This guy obviously is a difference of cubes. We've got 2x all cubed minus 4 cubed. Okay, and that's equal to, so this is a difference of squares, so we're using this guy now. So that's equal to a minus b times a squared, so that's going to be 2x squared, so 4x squared, plus, right, it's a plus this time, plus a times b, so that's going to be 2x times 4, so 8x, and we're going to have plus b squared, so 16. Okay, so all we're doing is plugging numbers in where they go. Okay, so now we're on to EQ4. What is the fundamental theorem of algebra and how can we apply it? So the fundamental theorem of algebra in like actual math speak is actually more complicated than what I wrote down here for you, but this is the more proper way of defining it. So if I have a function, p of x, right? P is a function of x. And this function of x, and I'm not going to use that. This function of x is an nth degree polynomial such that n is greater than or equal to 0. And I should also say, besides that it's greater than or equal to 0, n is also a natural number, meaning we're going 0, 1, 2, 3, 4, etc. Okay? So p of x looks like your standard form polynomial. Ax to the n plus bx to the n minus 1 plus cx to the n minus 2 plus blah, 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 blah. Okay, on and on and on and on and on. Okay, so what we're saying is, if a polynomial of nth degree is written out in standard form and all this and that, and it can be expressed this way, okay, that it's going to have precisely n linear factors that are on C. Okay, so what do I mean by on C? C is the set of what do you call it? Complex numbers. Okay, so that means it could literally be any number that we've learned about. Okay, so I know this probably just seems like a bunch of abstract gibberish, so let's look at an actual example where we're going to apply this. So here we have a polynomial function, namely f of x equals 3x to the third plus 2x to the second plus 6x plus 4. So this is written out in standard form. Okay, so this is just like our p of x here. Okay, and we're first asked to find the linear factors of this function. Okay, so the linear factors. So that means we're going to have to use grouping. Okay, but it says linear. So all of our factors need to be to the first power. Okay, they need to be expressed as first degree polynomials. Okay, so first of all, let's take note right here. This polynomial is a third degree polynomial. Okay, so let's keep that in mind. So according to the Fundamental Theorem of Algebra, if it's a third degree polynomial, that means that it's going to have 3 factors. Okay, it's going to have 3 linear factors. Okay, so let's see if the fundamental theorem is true or not. And obviously, it's already being called a theorem. Obviously, it's true. Anyway, so let's go ahead and factor. So I can go ahead and rewrite this. So here on the left, my GCF would just be x squared. And I'm left with 3x plus 2. On the right, my GCF is 2, apparently. So we're going to factor out a plus 2. And that's going to leave me with 3x plus 2 again. Okay, so now I've got 2 terms. And the GCF between them is the 3x plus 2. So that's what I'm going to factor out next. And that leaves me with x squared plus 2. Okay, so now what? This is not a linear factor. Okay, so the simplest way to go about this, if you need to factor this guy further, which we do, the simplest way to go about it is to just set it equal to 0. Okay, you'll get x squared plus 2 equals 0. And just solve it for the x. Right, so then we've got x squared equals -2. Take the square root of both sides. X equals plus or minus the square root of -2, which means it's imaginary, so plus or minus I square root of 2. Okay, so that means this guy here factors out into both x plus I square root of 2 and x minus I square root of 2. Okay, so how many factors do we have? Holy dog crap. We have 1, 2, 3. And remember, n was equal to 3. Now, number 2 is asking us, does this prove the fundamental theorem of algebra. Let's go back. What else do we need? Is our nth degree, right? Is our degree on the set of natural numbers? Well, yes, it is. Okay, so n is on n, right? So 3 obviously is an element of the natural numbers. So we're good there. Is 3 greater than or equal to 0? Yes, it is. Okay, so does this prove the FTA, the fundamental theorem of algebra? Yes, absolutely. Okay, so now we're asked, what are the zeros? What are the zeros or the roots? That's another, and I actually wrote that here. I don't know why I had to write it again. Okay, so when you hear us asking for the zeros, we're asking for the roots and vice versa. Okay, so anyway, we just need to find the solutions for these 3 factors. Right? So obviously our answer here, 3x plus 3. If you don't remember, so all you do is just set these all equal to 0. Okay, so 3x plus 3, we're going to end up with x equals negative 3 over 3, which is negative 1. Okay, so one of our roots is negative 1. Okay, what about the other ones? Well, let's see. Oh, I'm an idiot. You guys watching the video probably caught this. So this is 3x plus 2, and then I put 3x plus 3 here. Yeah, I thought something was off because I didn't remember it being 1. So that's a 2. So that changes what we're going to get for that first root. Whoopsie! Okay, so I just need to change that to a 2. Okay, so that's just going to end up giving us x equals negative 2/3. Okay, so let's see if I can, yeah, now that looks stupid. So our first root is negative 2/3. Okay, then our second root, so we already saw what it was over here. Here's our guy right here. So our next one is going to be positive I square root of 2, right? That would go to this guy here. And our next one is going to be negative I square root of 2. That would go to this guy here. Okay, so those are our 3 roots. Now, number 4 is asking us, could we also say that these roots are our x-intercepts? And the answer to that is yes, absolutely. Okay, so I've got a little link here for Desmos. Let's see if it pulls it up all stupid on the wrong screen or not. Nope, it did a good job. Good job, Desmos. Okay, so that's the only thing it did that I didn't like. So roots or zeros are also our x-intercepts. Okay, now we only had one real root right here, and that was this negative 2/3 here. Okay, that was our only real root, which means that's the only number that's going to show up on a Cartesian coordinate plane of real numbers. And here we see it right here. So this negative 0.667, it's actually just rounded off. It's actually repeating 6's on and on and on forever. That is also just negative 2/3. Okay, so that right there to me is proof positive. These other 2 roots that involve complex numbers or imaginary numbers, right? Obviously, they're not going to appear on our graph, right? Because they're imaginary. This graph only pertains to real numbers. Okay, and I'm not even going to try to break your brain there. There will be better examples on your homework than that one. Okay, but the point is, so there's more than one name. So these are our factors, right? These 3 numbers here. Okay, I didn't want for it to do that. But these 3 numbers here, the 3x plus 2, right? That's 1 factor, 2 factors, 3 factors. Those are our 3 linear factors of the original polynomial, right? Those 3 factors give us 3 different roots, right? The real root of negative 2/3, that's 1 root. The complex root of I square root of 2 and of negative I square root of 2. Those are your second and third roots. Okay, those roots, or zeros, are also the x-intercepts for the graph of this function, right? Just to kind of summarize in case I lost anybody. Okay, so almost done. So now let's look at a few more examples. Okay, so we're being asked to find the roots of g, right? So this guy here, easy peasy. What we can do with this guy, g of x, we can go ahead and think of x to the fourth minus 16 as a difference of squares. And remember, a difference of squares looks like this. A squared minus b squared is equal to a plus b times a minus b, right? So if I go ahead and say that the x to the fourth is also equal to x squared squared, right, by the power rule, okay, I can go ahead and use the difference of squares formula here. Okay, or you can use what's called substitution. I was going to show you that, but now I think we're better off just leaving it like this. So I'm going to go ahead and rewrite that. So that's x squared squared minus 16 is equal to 4 squared, right? And then I can rewrite that into this over here. So that would simply be x squared plus 4 and x squared minus 4. Okay? Now, if we want to find the roots, we need the linear factors. These are not linear factors. These are quadratic factors. So we can factor this even further, right? So this guy on the right, that's easily going to factor into another difference of squares. So that's going to give me x plus 2, x minus 2. This guy on the left is a sum of squares. Okay, that goes back to imaginary numbers and actually what we just saw earlier. If you have a squared plus b squared, that's equal to a plus bi times a minus bi. Or, when all else fails, just set it equal to 0. X squared plus 4 equals 0. First, I want to use this though. Okay, so if I go ahead and do a plus bi times a minus bi, I already know I'm going to have x plus 2i times x minus 2i. Okay, let's see if we get that when I just set it equal to 0 like I am here. So subtract 4 from both sides. Take the square root of both sides. And holy dog crap. I get the exact same thing, x equals plus or minus 2i, and that's what I've got. Okay, so I'm going to go ahead and say x plus 2i times x minus 2i. So I have 1, 2, 3, 4 linear factors, and lo and behold, n equals 4. So that's just further proof of the fundamental theorem. So I should have 4 roots, right? So two of the roots are going to be 2i, negative 2i, right? We saw that here. The other 2 of the roots I'm going to get are real. Those are going to be negative 2 and positive 2. And again, 1, 2, 3, 4. That's equivalent to the degree of my polynomial. That is, so n is a natural number greater than or equal to 0. Okay, let's do it again. Let me erase a little bit, give myself some room. Let's see. Find the roots of h. So here's h. This guy is obviously a difference of cubes, right? So I have a cubed minus b cubed. Okay, and I can factor that into a minus b times a squared. Remember, it's plus now, so if we go back and look, I don't remember which page I had it on. So if we go back and look here, right, it's minus and then plus. Okay, so a squared plus a times b, so that's going to be 4 times x, so plus 4x, and plus b squared. So that would be 16. Okay, so now this is where it's going to get kind of tricky. I have to do the linear roots of this guy here. Okay, so AC grouping is not going to work because there's no factors of 16 that are going to add to give me 4. Okay, so we're going to have to do, completing the square is going to be the easiest thing to do. Okay, if you're not good at completing the square, you can use the quadratic formula also. Okay, but we're going to go ahead and just complete the square. So I'm going to take this guy off to the side over here. So x squared plus 4x plus 16, right? So we've got our x squared here. And then we have our, so we need to cut this in half. So this is going to be plus 2. This is going to be plus 2 also. Okay, then we just need to actually, so then we're going to have 2x and 2x. Then we're just going to have to actually complete this little notch in here, right? And this side is going to be 2 by 2, so that means this guy here is 4. Okay, so what we're going to go ahead and do, our square completer is going to be plus 4, so we're going to have x squared plus 4x plus 4. We have to do minus 4 also because we can't just pull that out of nowhere, right? And then we still have to bring down the plus 16. Okay, so this guy is the area of this square that we just completed. So that's just going to be x plus 2 all squared. And then we just combine these two like terms, plus 12. Okay, so if we just set that equal to 0, we'll get our factors from this. And there's going to be 2 because it's a quadratic. Okay, so set that equal to 0, right? And I'm going to have to come up here. I'm running out of room. So I'm going to have x plus 2 all squared equals negative 12. I subtracted 12 from both sides here. Okay, then I'm going to take the square root of both sides. So x plus 2 is equal to plus or minus the square root of negative 12, or plus or minus I square root of 12. Okay, then I'm going to subtract 2 from both sides. So negative 2 plus or minus, and then we're going to have, so this 12 can factor out into 2I square root of 3. Okay, so those are going to be all of our, and that one was gnarly. So what are our factors? So let's go ahead and write this out. So I'm going to go ahead and have then x minus 4 times x, let's see. Okay, stupid Siri keeps going off. Okay, so anyway, that's going to split into x plus 2 plus 2I squared root of 3, and the other factor is going to be x plus 2 and then minus 2I squared root of 3. Okay, so that would be our 3 linear factors, and our actual roots are going to be, so first root is going to come from here. That's going to be x equals 4. And our second root is going to come from these guys. So that's going to be negative 2. And then plus 2I squared root of 3. The other one is going to be negative 2 minus 2I squared root of 3. Okay, and we have to express them out this way. I know it sucks, but we have to express these complex ones out this way because your calculator can't give you a decimal estimate, not for a complex number. It's not smart enough, and neither is our little human brains. Okay, so let's go ahead and do one more example. And looking at it, we're looking at m of x. Looking at it, we're going to have to do sum of cubes there. We think. I don't know. Let's find out. So we're here. Okay, so what we're going to want to do is rewrite it. So x cubed plus, so what is the cube root of 216? And off the top of my head, I'm pretty sure that it is 6. Yeah, it is 6. Okay, so x cubed plus 6 to the third. Okay, so we have that written out as a sum of cubes. So we're going to have a plus b times, remember the plus and the minus get switched around. So I'm going to have a squared minus a times b plus b squared. Okay, so there's one of our linear factors. We're going to need to get the other two from here. And you'll notice anytime you have to factor out a sum or a difference of cubes, you're always going to get one real root and two complex roots. Okay, so these two right here are going to end up being complex. And I'm going to go ahead and complete the square. I'm not going to draw it out this time. Okay, if you still need help with that, go ahead and let me know. But yeah, I'm going to try and save time on this video. So this guy is going to become, so this is going to be x, let's see here, minus 3 all squared. Make sure I'm doing that right in my head. Yeah. And then that's going to give me a plus 9 minus 9. So that's going to be 27. So plus 27 equals 0. Okay, so then my factors are going to come from me actually doing this. So this is going to be x minus 3 is equal to plus or minus I times the square root of 27. And I'm skipping a whole bunch of steps here. Then I can go ahead and factor this further. So this is going to be equal to x equals 3 plus or minus is going to be 3i square root of 3. Okay, so my three linear factors, x plus 6, and then we've got x minus 3 plus 3i squared root of 3, and also x minus 3 minus 3i squared root of 3. Okay, so my actual roots from this are going to be negative 6. That's the root I'm going to get from this factor. And then I'm going to have, so these are my answers for that one there. So 3 plus 3i squared root of 3, and then 3 minus 3i squared root of 3. Okay, so those would be my three roots there. And number 4 is just asking, did the FTA check out again? And the answer is absolutely, right? G of x had 4 roots, 1, 2, 3, 4, from 4 linear factors that we got. Okay, h of x had 3 roots from 3 linear factors that we got. And m of x had also 3 factors from 3 roots that we got. Okay, so all in all, oh, we didn't answer EQ5. Let's come back to that. So that is a goof I'm going to have to fix. If only I could find my mouse. Okay, so I have that goof fixed. So let's go ahead and answer EQ5. So now we're going to talk about how we can basically work backwards. And I don't know how I left this slide out. Anyway, so what we're basically going to do is work backwards from what we were doing on the previous slide, right over here, right? So we were finding roots from a polynomial. Well, now we're going to find a polynomial from the degree and the roots. Okay, so number 1, we have a third degree polynomial, and its 3 roots are 0, 2, and negative 3. So that one's going to be relatively simple. Okay, so that means, and I'm just going to call it f of x. That means our f of x here, it's going to have the factors of x times, and I'm not going to put the bullet, x times x minus 2 times x plus 3. Okay, the x comes from the fact that one of the roots is 0. The x minus 2 comes from the fact that one of the roots is positive 2, right? Because if I set x minus 2 equal to 0 and I solve for x, I get a positive 2. Okay, so you get the idea. This isn't new. We've done this before, just not with anything higher than a quadratic. Okay, so let's look at the next example, number 2. And actually, here, let's go ahead and multiply this out, because this is what I'm going to expect you to do in your homework anyway. So what we would do, distribute the x, so x squared minus 2x. Okay, then we're going to FOIL what's left. So that's going to be x to the third, right? And this is going to be plus 3x squared minus 2x squared minus 6x. And that's going to leave me with my answer, x cubed plus x squared minus 6x. Okay, so my actual f of x here would be this guy that I just got. And I'll go ahead and write it down. So f of x for number 1, x cubed plus x squared minus 6x. So it's a third degree polynomial with the 3 roots 0, 2, and negative 3. Okay, so easy peasy. We're just working backwards from what we've been doing already. My phone is driving me crazy. I can say like Jupiter and it thinks I'm talking to Siri. Okay, so I need to match colors here. So n equals 4, so that means it's 4th degree, and its roots are plus or minus 1, that's 2 roots, and plus or minus 5, that's 3 and 4. Okay, so what I end up with is f of x is now equal to x plus 1 times x minus 1. That accounts for the plus or minus 1 times x plus 5 times x minus 5. Okay, and I'm going to take a little shortcut here. These two are both expressible as differences of squares. So that's just going to be x squared minus 1 times x squared minus 25. Okay, and then I'm just going to FOIL there. X to the 4th minus 25x squared and minus x squared and plus 25. So I'm going to end up with, when I combine like terms, x to the 4th minus 26x squared plus 25. Okay, so go ahead and write that down for my answer for my second example. And I mean, all we're doing is just piling on top of what we already know. We're just building on top of it, right? We're not really doing anything new per se, just little things here and there. But more than anything, we're just expanding upon what it is we know how to do already. Okay, so third degree polynomial, and these are its roots. Okay, so we're going to have f of x is equal to x minus 3, because its first root is positive 3, x minus 4i, because its second root is positive 4i, and x plus 4i. Okay, so this right here, I'm going to treat that like it's a sum of squares, right? So that's going to be x squared plus 16. So this is x minus 3 times x squared plus 16, right? And again, the sum of squares, I get that from a squared plus b squared is equal to a plus bi times a minus bi. Again, it's a great idea to memorize these things because it makes things a lot easier, okay? Then I'm going to FOIL. So that's going to give me x cubed. That's going to give me 16x minus 3x squared and minus 48. Combine like terms where applicable, and there isn't any. Write everything in standard form, aka descending order, and we get that f of x is simply x cubed minus 3x squared plus 16x minus 48. Okay, and last example. Go ahead and erase this. I don't know why I didn't. Okay, so we've got a fourth degree polynomial whose roots are 2, -5, and -4 is multiplicity 2, or a double root. So this is important. You need to see this. You need to see what multiplicity 2 means, or multiplicity in general on a given polynomial and its roots. So fourth degree, so f of x, and this is nice, I'm going to have all this room now. F of x is going to be equal to x minus 2 times x plus 5 times, so what does this mean? -4 is multiplicity 2, right? Well, what that means is that it's a double root. It's the simplest way to put it, or it's just there twice. So it's going to be x plus 4, right, because it's minus 4, x plus 4, but it's going to be squared. It's going to be there twice, right? Or you can think of it as x plus 4 times x plus 4. And that's how I'm going to need to write it anyways, because I'm going to have to FOIL all this nonsense out. So I'm going to go ahead and do that. Okay. And this is another shortcut we can take here. This is going to be a perfect square. Perfect squares are always, so when you've got a plus b all squared like this, right? It's always going to end up being a squared plus 2ab plus b squared. Okay? And that's pretty much how it's always going to work out. Okay, so what we're going to do here is apply that. So we're going to have x minus 2, x plus 5. This is going to become x squared plus 8x plus 16. Okay, saves me some time. Again, memorizing this kind of stuff is super helpful. And I actually memorized this from just completing the square, right? A perfect square always works out that way. Now we just need to FOIL all of this out. So I'm going to have x squared minus 2x plus 5x minus 10. Combine like terms, x squared plus 3x minus 10. And we're going to multiply this by x squared plus 8x plus 16. And we know how to FOIL these guys. So x squared times x squared, x to the 4th, right? We're going to distribute each term. Okay, so times 8x is going to be plus 8x cubed, and then plus 16, plus 16x squared. Okay, then we're going to do 3x. So plus 3x cubed plus 24x squared and plus 48x. Okay, and let me erase her here. I'll just use a different color now. So now we just need to do the minus 10. So -10, so minus 10x squared minus 80x and minus 160. Okay, so now we're just going to combine all the like terms. So x to the 4th, it's not going to combine with anything. We have x to the 3rd, 3x to the 3rd, so that's going to be plus 11x to the 3rd, 16x squared, 24x squared. That's going to give me 40x squared. Okay, 48x. We forgot the minus 10x squared. Dag nabbit. So that 40x squared is going to combine with the minus 10x squared to give me 30x squared instead. Okay, so now plus 48x minus 80x, that is going to leave me with, so that's going to be negative 32x. And we're left with the constant minus 160. So f of x is equal to this guy here, a fourth degree polynomial with these four roots, 2, negative 5, and 4, negative 4, with a multiplicity of 2. Okay, so when you see multiplicity of 2, remember that just means it's a double root. That means it's there 1, 2 times. And later on in college algebra, you'll see multiplicity 3 or multiplicity 4. You know that just means it's going to be there that many times. Okay, so now that we've answered EQ5, okay, this video is completed. If you have any questions, obviously send me an email. Otherwise, let me know in class. Goodbye.